Hello, my name is Niklas Hjert, and I will give you a short demonstration of Water in Europe Today, which is a web application developed by the Swedish Meteorological and Hydrological Institute for the Switch On project. Well, what does WET do? WET visualizes data from any hydrological model. For now being it's EHYPE, a hydrological model of the European continent, developed by the SMHI hydrological group, but really any hydrological model with open data could be visualized. The purpose of WET is to give the user an understanding of how the current and forecasted discharge relates to historic discharges for any specific point in Europe. The application has two components. It has a map component, which is what you see when you open the application, and it has a diagram component. So the first thing you need to do when you enter the application is to choose your area of interest. You do that by zooming and clicking in the map. Let's go, for instance, we are interested in, well, let's say we're in Dresden. I would like to see the discharge at Dresden in the upper Elbe catchment. I click on Dresden, and what you see now is a highlight of the hydrological network upstream of Dresden. That is where the water comes from, but also it highlights the path of the Elbe down towards the Atlantic Ocean. And if you zoom out, you can see the coastal line and where the Elbe enters the Atlantic. Well, as you can see in this example, there is a lot of blue color in the maps, and the blue color means that discharge at a specific point is above normal or much above normal for this time of year. You can get some more information about this if you hover over the legend. You can see that the deep blue color means that discharge is above the 90th percentile for this date. If it's a more of a light blue color, it's above the 75th percentile for this date. If, on the other hand, it's a red color, light red means below 25th percentile for this date, and the deep red is below the 10th percentile for this date. So what does this mean? Well, to explain more of this, we need to see the diagram. So click on Show Diagram on the upper left corner, just below the legend. Now, the bottom edge of the screen is filled with a diagram of the selected point of interest. In this example, it's Dresden. It shows you the current and forecasted discharge with a solid black line, and there is a thin vertical red line indicating the present day, the 5th of June in this case. In the background you can see some light blue shades, blue lines, and this represent historic discharges at Dresden. Now you can see that for most part the black line is quite far above the blue shades, which means that for now discharge at Dresden is higher than normal for this time of year. The normal range is calculated from discharges between 1981 and 2010. Now, if we're interested in other points in the catchment, either upstream or downstream of Dresden, we can just click on any of the points and you will get a new diagram plotted for that specific point in the lower part of the screen. You could also click downstream of Dresden to see the discharge in Elbe. And the last thing I wanted to show you here is the time slider, which is in the upper left corner just above the legend. The time slider makes it possible to switch dates in the map view, so you can actually step through different days in the forecast, and you see on the map that it's actually drying up. A lot of the blue colors are disappearing, and we are entering what seems to be a normal range at the end of the forecast period. Also, you can see that the thin red line in the diagram moves when you click on the time slider and you move the time slider. It actually shows the corresponding date in the diagram as well. Now, the last thing I want to show is if you're interested in another area, you can change the point of interest by either clicking Change Area in the upper left corner of the screen, or simply drag the flag with the mouse and releasing it on another area. And you can start investigating the flow in this particular area. Thank you very much. Hello, I'm Niklas Hjert and I'm going to give a brief demonstration of the European Eutrophication Control, a web application developed by the SMHI for the Switch On project. The purpose of this application is to provide an analysis and scenario tool for eutrophication of inland waters. The application visualizes nitrogen and phosphorus transport calculations by the EHYPE hydrological model. These calculations will reveal the sources of nitrogen geographically and sector-wise for any point in the catchment. Now, the first thing that you need to do as a user is to define your point of interest. For this purpose, let's choose a catchment, for instance, in Italy. Let's choose the Lago di Como, just north of Milan. As I select this lake, a graph is highlighted on the screen, and you can also see a source apportionment on the right hand corner for Lake Como regarding the phosphorus transport. You can also switch to nitrogen, and you can see the source apportionment for nitrogen immediately. Let's go back to phosphorus. Now, what the graph in the map is showing is the relative contribution from each of the catchments upstream of Lake Como to Lake Como. So each of these circles now defines the accumulated load of phosphorus at this specific catchment. So we can see here that quite a lot of phosphorus is coming down River Adda in the northern part of the lake. We can also see the total sources, total phosphorus load at the outlet of Lake Como. The pie diagram in the right hand corner is showing us that the biggest contributor to phosphorus in Lake Como is the agricultural land. We can also select agricultural land on the left hand corner, and we can see the relative contributions of load from agricultural land to Lake Como. We can look at other sectors such as rural households, wastewater treatment plants, industry, and urban areas. Let's go back to all sources and just look at the second choice. You can actually choose what load to visualize. The current load is the accumulated load in each part of the catchment, but if you switch to the local net contribution to the point of interest, you will see how much each of the catchments is contributing to Lake Como. Okay, let's switch back to the accumulated load. And now let's think about measures to reduce the phosphorus load on Lake Como. Imagine, for instance, that we can plan a measure somewhere on River Adda to reduce the phosphorus loads on Lake Como, and we can test this by clicking on one of the catchments in River Adda, and we can see here that River Adda is yielding 130,242 kilograms per year to Lake Como. Let's say that we can reduce this in some magical way by 50,000 kilograms. So let's type in minus 50,000. Now you can see that the outlet figure is much reduced. It's now to 80,000 kilograms per year. And you can also see that in Lake Como, this actually means a 17.71% decrease in phosphorus load. Please note that you don't have to tell exactly what kind of measure you're doing, just the result of this measure and how it's affecting the point of interest. You could also enter other scenario or other measures. For instance, here we may be able to reduce the load by minus 10,000, and up here we might be able to reduce it by 2,000. what you can see now is all of these scenarios together will give a minus 21.96% decrease in Lake Como. I should add that you could also simulate an increase in load. For instance, if someone is planning building projects or golf courses in the catchment, this figure of minus 10,000 might turn out to be plus 10,000. So you can add 10,000 kilograms and you can look at the resulting load on Lake Como. And you can remove the scenarios by just clicking out the boxes, or you can mail the scenarios to someone else by choosing the link and then copying the web link and mailing it or sharing it with someone else. One last thing is that this is a highly interactive tool. You could also move the point of interest easily by selecting the flag and pressing your left key on the mouse and just dragging it to another point. And now you will have analysis of the source apportionment for this point, and you can see to the right hand corner what the circle diagram or the pie diagram is telling you about the sources. There is also a filter function which allows you to remove points that are not interesting for some reason. You can remove the small catchments with small contributions and to focus on the catchments with the larger contributions. Well, that's all for now. Thank you very much for listening.
Introducing a GIS-based European Small Hydropower Atlas, a tool for technical and economical feasibility assessment of small hydropower plants. With this tool, the user can estimate hydropower productivity on the basis of flow, jump and environmental flow. Rank sites for the development of small hydropower plants, considering where infrastructure may be a limiting factor. Screen for costs and optimal sizing of the plant. The tool is being developed using a raster-based approach. That means that all relevant information come in the form of a raster map, starting from hydrology. Hydrological information is given at this stage of development by the EHYPE model, hydrological model prepared by Swedish Meteorological and Hydrological Institute, that gives hydrology all across Europe on a basin or sub-basin level. What we need to do was to downscale this information down to the river network. And we did it using drained area in order to rescale hydrology. At this point, the user knows virtually for every pixel along the river network the flow duration curve, and can make some hypotheses. For example, selecting the environmental flow and deciding which is the design flow, in order to estimate the total derivable volume for hydropower generation. Next variable of interest is the jump downstream along the river network. We estimated the jump by processing the digital elevation model with tau dam algorithms. First of all, we evaluated a depressionless dam, and then we calculated flow direction and flow accumulation. At the end, with the slope average downstream function, we evaluated jump downstream along the river network. The tool is being developed using a multi-level approach. At level 1 we used low-resolution digital elevation model, while at level 2 we used much more detailed digital elevation models, available for free. Level 1 gives a productivity indicator with annual potential energy given a 1 km downstream diversion length and jump, for river segments with a minimum drained area of 10 square kilometers. Such an indicator is good for screening purposes, regional large-scale assessment, or ranking of suitable regions, and can be aggregated over a national or regional basis in statistics. Level 2 gives a productivity estimation using much higher and much more detailed digital elevation models. Such productivity estimation is the annual potential energy for river segments that drains an area down to 1 square kilometer for assigned diversion lengths downstream. This information is good for site scouting and down to feasibility study. That is what comes immediately before preliminary design.
The Hydropower Atlas has been developed as a web mapping application. The components of the web mapping framework are a geospatial database where all the spatial data are stored, a set of Python routines requested for the energy and feasibility computations. This geospatial database is able to be connected with the Virtual Water Science Laboratory Open Data Database. The results of all the computation are available through a web mapping server developed using the OpenLayer technology. Finally, the graphical user interface consists in a web mapping application accessible through a standard web browser. In the next frames of the video, is presented a demo of the web mapping application developed for the hydropower atlas. Thank you very much for the attention, and see you in Rimini for the General Assembly in September.